Okay, so let's review for the Unit 8 exam, work in energy. The first thing we did, we started off by defining what energy is. Energy, it's just the capacity to make change to the or in the environment. Environment. Something has energy, it can cause change. If something doesn't have any energy, it basically can just sit there and exist. Now, we said that energy can be stored in the environment somehow. And we talked about several ways of doing that. One of the ways is kinetic energy. Here the energy is stored up in the motion of an object. So here we have like a rock, and maybe you've thrown a rock or something. Or maybe this is a comet flying through space. Doesn't matter. It has mass, and it's moving, at least with respect to some observer, and therefore it has kinetic energy. And we derived an equation for kinetic energy. K equals 1/2 the mass times the velocity squared. We have gravitational potential energy. And we said this is energy stored in a gravity field based on an object's position in that gravity field, or particularly here, let's take the same rock and put it above the ground. Well, it's basically how much work gravity can do to get it to the ground, or to get it to some reference. You have to measure its height from somewhere. And we call this U sub G. What does the U stand for? Potential energy. I don't know why we use the letter U to represent potential energy, but we do. Very common variable name for potential energy. The G refers to gravity. And now, how much work can it do? And we haven't defined work yet, but we will in a minute. Well, it's the force times the displacement, mgh. Now, here's the one thing where gravity can be, or gravitational potential energy can be negative, is what if I have a hole in the ground? Like maybe I've thrown this rock in the bottom of a well. Maybe there's a rock down here in the bottom of the well. Well, if we say that gravitational potential energy is 0 at this point, that is, we're measuring height from the ground right here. Here, we're below the ground. So just to get to 0, gravity's going to do negative work, right? The force is down, the displacement's up, so the work done is negative. So unlike kinetic energy is always positive. Gravitational potential energy, if you're above the ground or above your reference, it's positive. If you're below, it's negative. Make sense? Sort of? Kind of? Okay, then we had some other ways of storing. We don't really have an equation for them, or we didn't develop one. But we have elastic potential energy. And this was the energy stored up in a stretched or compressed material. Like a spring. You stretch a spring. You've stored energy in that spring. That spring can now affect change to its environment, right? You let go of the spring and shoo, you have a pellet gun, a spring-loaded pellet gun. You pull the spring back, lock it, there's potential energy there. You put a little pellet in there, release the spring, boom. That spring will do work on the pellet, give it kinetic energy and so on, but it can affect change. Then we have some others. Chemical potential energy, Oh, this we call U sub E. Chemical potential energy. Didn't really have a variable name for that. We just talked about it. This is the energy stored up in the way molecules are arranged. Gasoline has a lot of chemical potential energy. Carbohydrate, sugar, that kind of stuff. Very common in biology to talk about chemical potential energy. Yes?
In a battery, would that be chemical potential?
Yes, a battery. The question was, is a battery chemical potential energy? And absolutely it is, yes. Lots of different forms of chemical potential energy. Energy stored in the way atoms are arranged. So if you think of atoms as being like little objects with little springs and hooks, and you push the spring together and you hook it together, and now if you release that, the atoms will fly off. Now if atoms are flinging off, if they're all moving in random directions, we call that, I can squeeze it in here, thermal energy. And this is energy stored in the random motion of molecules. Now, think about it. Everything's made out of molecules, right? Kinetic energy, so an object's moving, okay, it's made out of molecules, so all its molecules or atoms or whatever are moving, but they're all moving together, right? They're all moving in the same direction. Thermal energy is all the atoms, they're together, but they're all vibrating in different directions and so on. It's all kind of scrambly. But there is energy stored in it. If you don't believe it, just stick your hand in hot boiling water, and you'll find that the thermal energy of the molecules can affect change to the skin on your hand. I actually poured hot coffee on my thumb a few months ago and kind of scalded it pretty bad. So that was thermal energy affecting change. Okay, and that's about it. Now, energy can be transferred. So let's talk about, let's center this back again. Energy can be stored, and energy can be transferred. Yes? No. The question was, do we need to know the equation for elastic potential energy? No. That will not be on the test. Okay, energy that's transferred. Several ways of transferring energy. One of them is heating. And we're going to talk about that in Unit 9. So you don't need to worry about it for this test. There's radiation, or electromagnetic radiation and that sort of thing. There's electricity is a way of transferring energy from one thing into another. We're not going to really worry about those right now. Right now, there's one way of transferring energy that you are going to have to work problems and thoroughly understand, and that is work. Work or working. If you're doing work, you're working. Or now work is when you transfer energy through the application of a force. Okay, so, and we said the equation was force times, or dotted with displacement. Why did I try to squeeze it in? Displacement. I'll just abbreviate it like that. Work equals force times displacement, or dotted with displacement, or work equals the magnitude of your force vector times the magnitude of your displacement. I'll use delta x for displacement, but it can be delta y or delta r, whatever you want to use to represent displacement, times the cosine of the angle that the force vector and the displacement vector make when you put them tail to tail. Now, what is work? Work is when you're transferring energy from one system into another, from one thing into another thing, by applying a force to it. And notice that this has units of newtons times meters, and that's a joule. Okay. Now, we looked at several situations where different kinds of force are doing work. So let's look back on that. So let's take a look at different kinds of work. Let's take a look at a cart here, and we'll put it on wheels, okay? We'll put it on wheels. Why? Because we want to say there's no friction in this problem. And let's say this has a certain mass, and let's apply a force like this. Here's F1. Say if somebody else is pushing it the other way, here's F2. But we'll say that F2 is smaller than F1. Now we know from the previous units that this object is going to accelerate to the right because there's a net force to the right. And I don't necessarily want to rederive that. It's just a clever little derivation. And you can go back and review that very first lecture on work where we developed the work energy theorem. So you will need to know this, the work energy theorem, which basically says the work done by the net force, or the net work done, will be equal exactly to the change in kinetic energy of the object. Now, what do we mean by net work? Well, let's say this thing displaces to the right by a certain amount. There's our delta x right here. And, well, look, this force is doing work. So the work done by F1 will be equal to F1 times the displacement, delta x. Now look at F1 and delta x. They are parallel to each other, right? They're in the same direction. So what's the angle between them? 0. So cosine of 0 is what? 1. And you better know that the cosine of 0 degrees is 1. So that just means, oh, okay, F1 times delta x will be the work done. But what do we know about the work done by F2? Well, look at F2. And again, we're not plugging in any numbers here except for the angle. So that's F2. And we're displacing delta x. But what's the angle between to the right and to the left? That is 180 degrees, right? And so what does this mean? What's the cosine of 180? It's not 0. Get your calculator out, make sure it's in degrees, and go the cosine of 180, it's negative 1. Now what does that mean? Okay, it means it's doing negative work. Okay, so anyway, let's just do that. This is F1 times delta x, and I could give you numbers here, but I don't want to take the time to do that. Here's F2, but this is negative. Okay. And now here's what, this is positive work here, right? Positive. You see, some outside agent, a person, is pushing on this crate, and they're transferring energy into this crate, and they're trying to make it go faster and faster. They're trying to add to the kinetic energy of the crate as it moves to the right. Does that make sense to everybody? I mean, it should be obvious here. Don't make it more complicated than it is. This person is pushing to the right, trying to make it go faster and faster as it moves to the right. They're trying to add energy to this system. That is this little crate. But what is this person doing? They're going, whoa, not so fast. Literally not so fast. They're making it go slower. They're taking energy away from the system. As this guy tries to add, this is doing negative work. It's saying, no, I'm not going to give you all that work. they're probably creating heat. You know, if they're pushing on with their body, but so when you say positive work is being done, you're adding energy to the system. When negative work is being done, you're taking energy out of that system. Now, what happens if I add these two together? The work done by this force plus, oh, by the way, there's two other forces acting on this, right? Let's do that. There's the normal force. How much work is being done by the normal force? I almost skipped it. Well, how much work is done by the normal force? Well, it's the normal force, which is probably going to be mg, right? It's just supporting the weight, times the displacement. But what's the angle between the normal force and the displacement?
90.
And what's the cosine of 90 degrees? 0. Which means, look, this force is applying, but it's really not trying to transfer any energy into or out of the system. It's not going to make it go faster. It's not going to make it go slower. Same thing is true with gravity. You have mg going down. It's not trying, mg times delta x times the cosine of 90 degrees is 0. 0 work done. But conceptually what's happening is it's not trying to transfer. Now if it was falling down, gravity would be doing work. Yes, okay. But in this case, you're not. These two forces are not doing any work. And but these two forces are. This is doing, F1 is doing positive work, F2 is doing negative work, the normal force is doing 0 work, the gravity is doing 0 work. Well, the net work done is the sum of these guys. So this is, this work plus this work is the net work done. And what's that equal to? Well, let's add this. It's going to be F1 times delta x minus F2 times delta x. Well, we can distribute out or factor out the delta x. That's going to be F1 minus F2 times delta x, isn't it? But look at this kind of a free body diagram I've drawn there. What is F1 minus F2? What kind of force is that? Well, what do I get when I add up all the forces in a particular direction on here? We get the net force, don't we? Yeah, this is the net force in the x direction anyway. So this is the net force times delta x. That's the net work done. So now, and that will be equal exactly to the change in kinetic energy, or K final minus K initial. Now, I'm not, as I said, I'm not going to rederive the work done by the net force is equal to K final minus K initial. But if you know the net force on an object, and you can figure out how much work that net force is doing, it will result in a change in kinetic energy to the object. Okay? And the first couple of problems are work energy theorem problems. All right. Then we have what we call mechanical energy. And we just said this, and I did this when I did that Mr. Lake's Wild Ride thing, or with the beakers and so on. If you weren't here for that, sorry, there's no video for it. But if oh, that's not what I wanted to do. Hold on. If I have if I have an object, and I'm going to show an object like this. I'm going to say this could be kinetic energy plus however much gravitational potential energy it has plus however much elastic potential energy it has. You can think of, well, the definition of mechanical energy, E, is kinetic plus potential plus elastic potential. I mean, gravitational potential plus elastic potential. It's the sum of those. And so, if you have let's say let's say you have a roller coaster, and you start at the bottom, you go up to the top of the hill, maybe a little hill like this, and let's say you start at the top of the hill, there's the people and their hands are up, they're very excited. Well, if they're not moving, they have zero kinetic energy. And but they do have height. We'll call this H1. And so somebody had to do work to get them up there, but once you get them up there, let's say you have a certain amount of mechanical energy. So it's like that beaker is full. But there's no elastic potential energy here. There's no kinetic energy. But then gravity starts pulling them down. If gravity is the only force doing work on your roller coaster, and on the test, that's what I'm going to state. Gravity is the only force doing work on this roller coaster. Then what happens is that gravity, as gravity does work, gravity is the net force. Therefore, it changes the kinetic energy of your object. That's the work energy theorem. But as gravity does work, you lose gravitational potential energy, but you gain an equal amount of kinetic energy. And so what happens is that you're transferring gravitational potential energy into this other container. And when gravity does positive work, you gain kinetic energy. So this arrow right here represents the work done by gravity. Gravity doing work. So you are up the top of this hill, you go down like this. Oh, gravity starts giving you kinetic energy. When you're at the bottom of this hill, all of your gravitational potential energy has been transferred into kinetic energy. But then what happens? You start going up this little hill. Now gravity does work again, but gravity is down, right? The force of gravity is down, but your displacement is up. So gravity is doing negative work. When gravity does negative work, we lose gravitational potential energy and we lose kinetic energy and we gain gravitational potential energy when gravity does negative work. So here gravity's doing positive work, here gravity doing negative work. Now you can also have a problem where if you hit a spring, you lose kinetic energy and you gain elastic potential energy, or when the spring comes uncompressed, it does positive work and it turns that elastic energy into kinetic energy or even into gravitational potential energy. But if and only if, have you seen IFF before? If and only if, maybe in your math class. Gravity and springs. Now by springs, by the way, I can include rubber bands, elastic bands, bungee cords, whatever. If and only if gravity and springs are the only forces doing work. Well, if gravity and the springs are the only force doing work, all you're doing is transferring energy from kinetic energy to gravitational or elastic energy or back and forth, but the sum of all of these doesn't change. Right? The sum of them doesn't change. And therefore, you can say that mechanical energy is conserved. And therefore, if you have a problem like that, here's where you start. You go, oh, okay, the initial mechanical energy, or E1 if you want, like position 1, position 2, position 3, position 4, whatever, equals E2 equals E3 equals E4 or whatever. Or you can just say the initial equals the final energy wherever you decide to make the final energy. In other words, the mechanical energy doesn't change. And so what that allows you to do is set up an equation. Well, let's say I want to know what the height is here. You would say, well, initially I have mgh1. That's the only energy, because I don't have any kinetic energy or elastic potential here. But over here, it's split between the two. You go mgh3 plus 1/2 mv3 squared, because up here, the roller coaster obviously is still moving, and it has height, so it's got gravitational potential energy and kinetic. And now you can solve for how fast it's going. Very, very handy to be able to do that. Now, if friction or an applied force is doing work, well, then, then E initial does not equal E final. Because if something's doing work, let's say you motorize this thing, right? So the wheels spin and it adds energy to your, it adds mechanical energy to your system. Or if somebody comes along here and pushes on that roller coaster, it's going to add energy. Or as you're going down, there really is friction. Friction does negative work. It takes your mechanical energy away. And so so what you can do is figure out what delta E is. And I will give you a problem where I say, what's the change in mechanical energy of your system? Well, if you do that, then you just go, okay, E final minus E initial. Now, if you have friction or whatever, E final is going to be less than E initial. You're going to have negative change in mechanical energy, and that just means you lost energy. Simple. If it's positive, that means you added it. Like, let's take a look at this system. You have, imagine you have here's the ground. You have a swing. And you have a little kid. Oh, watch this. This drawing's pretty cool here. Here's a little kid on a swing, right? And they're going back and forth on the swing. Well, unless they're pumping their legs, if you just release the little kid, the kid will swing back and forth, right? Like a pendulum. And if you say, well, let's pretend this is a magical swing where there's no friction, this little kid will swing forever. Or until he or she crawls off the swing. But obviously, if you're on a swing, you got to keep it going. So you pump your legs and so on. But what if some adult out here pushes on the kid? Thank you. Miguel Pena, this is for you. So what if some adult pushes on this kid? Is the mechanical energy conserved now? No. This is an outside agent applying a force. This is not gravity doing work on the child. This is not friction doing work on... I'm sorry. There's no spring here. This is an outside agent. This is a person applying a force and adding mechanical energy to the kid. So the kid will swing higher and higher and higher with each push until they wrap around the swing. Okay? Or something bad happens. Usually when you're pushing a kid back and forth, you have to give a little push each time because there's friction taking energy out of your system. So the little push is there. You're adding energy to the system to keep the swing going, right? So anyway, so you have on the test, you'll have three major kinds of problems. If you have problems where you have to use the work energy theorem. Again, the work done by the net force will equal the change in kinetic energy. So you'd start there. Okay, there's a net force acting on my object. I need to know what the change in kinetic energy is or what the final velocity is or whatever. Start here. Or you'll have a conservation of mechanical energy, where the only force acting is the force due to springs or gravity. You would do this, E initial equals E final. So you would start here. That's your basic equation you would start with. And then you look for, like, okay, how much kinetic energy do I have? How much gravitational potential energy do I have? And then you solve for your unknown. And then you have change in mechanical energy problems. Let's say you've got like a skateboarder at the top of the hill, and they skateboard down to the bottom of the hill, and I tell you their height, and then I tell you how much velocity they have, but maybe they're not going as fast as they would if there was no friction. So you have to figure out a change in mechanical, that's delta E equals E final minus E initial. By the way, what would delta E be up here for conservation of mechanical energy? What would delta E equal if E initial and E final are the same? It would equal 0, right? And then of course, you'll have work problems. I'm sorry, that should have been the first kind. And the work problem is just force times displacement times the cosine of the angle between. Like, that's what work is equal to. There'll be problems like that. So these are the big ideas. And so you read the problem, recognize what kind of problem it is, and then start here, 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 or here. Depending on what's being asked for, they'll be very simple. I mean, it's actually computationally, anyway, it's not a very hard test at all. Any questions? That is all.